Hey folks, in this video we're going to talk about applications of electric and magnetic fields, and this particular one is going to be mass spectrometer. So a mass spectrometer, like let's say you're a CSI, a crime scene investigator, and you find this unknown substance and you want to know what it is. Well, if you ever watched a crime show, you'll see that they'll take the material and they'll vaporize it in some machine, and they all of a sudden the machine tells them what the substance is. How does that work? Well, the first thing you have to do is you have to vaporize the particles, you charge them up, okay, and then you basically accelerate them through a voltage. But when you accelerate the particles through the voltage, different particles, depending on where they were in the chamber, so like let's say this is your chamber here, okay, and let's say you set up an electric field going that way, okay, and let's say here's all your little vaporized particles, okay, and let's say you somehow charge them up, you make them positively charged, they'll accelerate to the right. Well, depending on where the particles started, they'll have different velocities when they get to the opening that you're going to let them go through, okay? So what we need to do is when a particle reaches this opening, we need to know how fast it's going, or we need to select particles that have a specific velocity. So the first part of a mass spectrometer is called a velocity selector. And here's how it works. So imagine you have an opening, and in that opening, one end or one part of the opening is positive and one part's negative. So that's going to create an electric field. Okay, so I'll call that E. Okay, and then you're going to fire your little positive charges into that electric field, and they're going that way. Well, if that were the only thing going on, the particles would feel a force downward, and they'd all crash into the bottom part of that device. So in addition to having the electric field, you also have the particles in a separate magnetic field, and they're in the same location. So that's a magnetic field. Okay, now if you do your right-hand rule, I've drawn the magnetic field on the page. If you do your right-hand rule, velocities to the right, so that your fingers, they curl into the page. That's your magnetic field. Your thumb points up. That's your magnetic force. Okay. So only the particles with just the right velocity, such that the magnetic force and the electric force are equal, will get through, and you put a little opening over here, and only those particles leave. And so you know their velocity. So the equation for this is really simple. You want the electric force downward on them to equal the magnetic force upward on them. So this is QE equals QVB, okay? And the Q drops out, and you get the velocity is simply equal to the electric field divided by the magnetic field. Okay, so that's the velocity selector part of the mass spectrometer. Now, what you then do, okay, is you have that device, so I'll kind of redraw it here, okay, and you have these particles that you now know their velocity, and you shove them into a second magnetic field. Now, I'm going to recreate this picture here. So we had positives up here, negatives down here. We had an electric field. Okay, so there's your E. And the magnetic field that I had here, okay, was into the page. I'll call that B1, okay? Because what we're going to do now is we're going to take those particles and have them go into a second magnetic field. Now this one I'll have pointing the other way. This is pointing out of the page at us. Okay, so like so, we'll call that B2. All right. So what's going to happen? Well, these little particles, when they hit that magnetic field, if you do your right-hand rule, your Lorentz force rule, they're moving to the right, so your velocity, your fingers point to the right. You twist your hand until your fingers curl out the page of the magnetic field. Now our thumb points down. So these little positive particles will feel a downward force. So they will turn in a circle and go kaboom against a sensor. All right. So here are the things that the numbers I'm going to give you, and then we're going to calculate what the mass of that particle is. So let's say this opening here, the distance from the positive and negative charge, well, I'll call that delta x. Okay, let's call that 1 centimeter. Okay, now by the way, all these numbers are made up. I don't know what they really are in the thing. Let's say that over here, I'll write B1. Let's say B1 is 100 Gauss. Let's say B2 is 6 Tesla. I just wanted to use different units for you. Let's say the change in voltage over here, this delta V to separate these charges, is 500 volts, okay? And finally, let's say you measure where these little guys crash into the screen. That's the diameter of that circle, and let's say it's 20.88 centimeters, okay? So with all those numbers, we're going to be able to calculate the mass of these little particles, and then we're going to be able to figure out what they are, okay? So the first thing I'm going to do is I'm going to do the velocity selector equation. So the velocity is going to be E over B1, and the E is the change in voltage over that delta X, and then divided by B1. So our velocity is the voltage divided by B1 delta X. Now, I'm not even going to plug numbers in. You can plug numbers in and get the velocity of these little guys. We're not going to need that, okay? Now, when they get into the circle, okay, so we're going to do net force equals MA. I'll do that over here. So you got net force equals MA. So that's QV V2 equals M, and then the acceleration is V squared over the radius, okay? And we'll solve that for velocity. So, I'm sorry, we're going to solve that for mass. So one of the V's drops out. And if you get the mass by itself, you would get Q, the charge, times B2, times the radius of the circle they're making, which is half of that diameter there, over the velocity, okay? Now, this is the expression for the velocity, so I'm going to shove that in there. So the mass is Q B2R over the change in voltage divided by B1 delta X. And I will simplify that complex fraction. You end up with Q. The B1 and delta X go to the numerator, so I'll write it B1, B2, delta X times the radius, all over the change in voltage that I had right there, okay, which was 500 volts. So we got all these numbers, all right? Now, oh, by the way, the charge, Q. We're going to assume that these are singly ionized particles. In other words, you've taken these atoms or molecules and you've charged them up, so you've taken one electron off of each one. So the Q is going to be one positive 1 electron, which is 1.6 E negative 19. So our numbers are the charge, 1.6 times 10 to the negative 19. B1 was given as, now it's 100 Gauss, there's 10,000 Gauss in a Tesla, so this would be 0.01 Tesla. B2 was given as Tesla, it was 6, okay, so 6. Delta X, that's the width of this tube, that's 1 centimeter, which is 0.01 meters. The radius of the circle, well, the diameter is 10 or 20.88 centimeters, so the radius would be 10.44 centimeters, or 0.1044 meters, so that's your radius. And then the voltage was given as 500. So if I divide this all by 500. All right, so that gives us an answer. If you do this, I get 2.0 times 10 to the negative 26 kilograms. All right, so that's the mass of our particles. So what on earth is it? All right, well then what you do is you got to figure out its atomic mass. So now we go back to a little bit of chemistry. So you take 2.0 times 10 to the negative 26 kilograms, okay, times 1 proton or neutron has a mass of 1.67 times 10 to the negative 27 kilograms. So then if you do the math here, I get about 12. So the atomic the atomic mass of this little particle is 12. Now, if you look at a periodic chart, what's probably going to have an atomic mass of 12? Well, if I look at my periodic table here, and okay, I'll zoom in, the atomic numbers are down here, and if you look at carbon, it's got an atomic mass of about 12, all right? So this is probably a carbon atom, all right? Now, larger atomic masses, you got to do a little more work to figure out what they are, because then they could be molecules. But this is the basics of how a mass spectrometer works. Now, for physics here, what I'm more concerned with is a combination of ideas. We have particles moving through an electric field. The force on a charged particle in an electric field is parallel to the electric field. We also have the particles moving through a magnetic field. Well, that force is perpendicular to both the velocity of the particle and the magnetic field direction. And then we use some combination of that along with some Newtonian mechanics here to figure out the mass of our unknown particle. So that's the main gist I want you to get out of this, is that we can combine multiple ideas in physics to make ourselves some tools. All right, I hope you found that video helpful, and thank you very much.